So hi everyone, so let's get started. So today we are talking about cross-validation. So particularly we'll talk about this so in the context of regression, we'll mostly talk about it kind of from the perspective of questions around polynomial regression. But this is kind of a major technique or viewpoint in like how people think about day analysis, and this applies to lots of other contexts. But we finally have kind of a like a good example now in polynomial regression, where we can really kind of look at the issues and kind of understand all the parts that are involved here. Okay, so let's start again by looking at the schedule for the class. We are the last week before fall break. There'll be this lecture, and then the next lecture, which will be the lecture on regression. I will cover all of the core parts of regression, kind of the most kind of important things that you'll need to know for this course, at least until we revisit it in the context of gradient descent. But in this lecture and in the previous two lectures, we have another one on Thursday. There's a quiz that day, so it's not like a full lecture. We'll in that lecture, we'll have some slack time. So I can partially do a review. So if you have questions about anything, you can ask me questions. But if not, I've got some other cool new insights that I would lecture on. I can talk about some views where kind of cross-validation has been kind of like the dominant view within like machine learning of how to evaluate things. But there's been some recent changes like in the last say like 5 years or so about maybe it's not always the right way to approach it. And so we can talk about that. I can also go through kind of the proof. We had the special equation of how you solve for the closed form for the optimal solution for least squares, linear regression, and so we can go through a little bit more detail why that's the case. But if you'd rather ask kind of questions about stuff, I can also open it to that on Thursday. Okay, so you also see the quiz 3 is on Thursday as well. This will cover the first 3 lectures of regression. It won't cover any of the stuff we necessarily talk about on Thursday, but there might be review stuff that's helpful, right? So it'll be covering these 3 lectures here. And so at this point, you know the drill pretty much with the quiz. I recommend you take it in class. It'll be a quiet time. You can ask questions. You can have a side sheet of paper that you can turn in on the quiz, and I recommend you kind of study by making this sheet of paper, and you can get up to 5 bonus points on the quiz for that again. Okay, the other thing is homework 3 is now posted. Okay, so it's homework 3 will be, it's due, it's not due until, let's see, until October 25th. So you basically have, over a week after fall break, so you don't have to spend all fall break working on it. But it's out early in case you want to spend time on it. It's going to be about both regression section and also gradient descent, which we'll cover after fall break. After the lecture today, you should be able to do kind of the first two questions. The first one is working through some examples in regression. And then the second one is more of kind of a question about kind of just reproducing the, kind of a question on what does regression actually mean? So trying to write out the mathematics. The third question is going to be on gradient descent. So we'll cover this kind of after fall break. Part of it is just kind of running an example of gradient descent. And then the second part is on what's going to end up being a more challenging function that we'll talk about. This is intentionally more challenging to try and solve this one, and you'll have to kind of, if you make a pretty good effort on this part, we'll give you basically kind of, if not full credit, most of the credit, but there's opportunity for extra points because it's like a bit more kind of, it might be a little bit more difficult than just applying some straightforward techniques. It'll make a bit more sense after you've seen the stuff in a regression, but I just want to preview that. Yeah.
So we should be expected to use Python to answer this?
Yeah. So in this assignment, we'll have questions 1 and 3 are explicitly meant to be done in Python. You could use other languages as well, but the TEs are prepared to help you in Python, and I'll be giving some examples in Python that will be a good kind of starting point for doing it. Yeah.
You said it's due on 25th.
I think it's due October 25th. Yeah, great. All this is on the assignment and on the webpage. Other thing I'll mention, this one, the first question 1 involves some data sets. These are pretty simple data sets, kind of like the ones we've looked at in class, but they are slightly larger. They're available on the links up here. I've not gone through how to load data into Python in class. This varies a bit. Like if you are doing this on your computer, just writing Python on the command line, which is how I learned how to do it initially. There's one way to do it. If you're using a notebook on your computer, there's another way to do it. If you're using Collab, there's another way to do it. This is one slightly tricky thing about Collab because it's a cloud service. You have to get the data into the cloud. I still kind of recommend using Collab if you haven't set everything else up. That will be fine for the rest of the class. If you have other stuff set up on your computer to run on your own desktop, that's on your own computer, that's also totally fine. But because this is a bit tricky, there are a couple of links here. These are also linked off of the web page, kind of up here. So a previous TA in the course put together a tutorial about the basic kind of stuff you would do, especially the loading of data sets within Collab. It's not, there's a couple of kind of tricks to it because you have to get the data into the cloud, but otherwise it's pretty straightforward. There's there's also a Python notebook that has the examples in there. That kind of walks through most of the examples, and then you'll be asked to do some slightly different stuff. If you don't go through this, we have or will go through enough Collab examples in class that you can do this slightly more manually by splitting the data and moving it around kind of by hand. This goes through a couple more things about how to do stuff with the data slightly more efficiently that we're just not going to spend too much time on in this course. But it's covered in this tutorial. There are plenty of other resources on the web. Again, I'm fine if you trying to figure out how to do something in Python, you look up some resources on the web. So how to do it. I don't want you to try and look up, okay, I found basically the same homework someplace else and someone posted the solution and I'm copying the solutions. Don't don't do that. We will try and look for that sort of stuff from known sort of solutions. But you can like, how do I figure out a command on how to do something that you're expected to kind of look up on the web? This is how everyone operates, even after you graduate, probably especially after you graduate. So that stuff is totally fine, and that's just an example of one resource. So also the help hours, the TAs have worked through a lot of this stuff and should be able to help you with these things as well. All right, any questions on the schedule? All right, so let's get into the lecture. All right, so we're going to talk about regression, and I revisit. Before I want to start at this, I want to revisit. So polynomial. So regression. Okay, and this is where, and we're going to look at the simple version of it, where you have x, y, and these are in or a subset of R cross R. So that means that this is a data set of these pairs x1, y1, x2, so y2 up to xn, so yn, right? And so each xi is just going to be a real value, and each yi is just going to be a real value. Right, and so then we can think of the simple plot. We don't need to worry about the high dimensional case, right? And so we're going to have in this plot, we're going to have these data points. Okay, so this might be x2, so y2, right? So we can think of this is the x2 value, and this is the y2 value. And if we're just doing so linear regression, we're going to fit a line kind of through here, trying the best fit line. But with polynomial regression, we can fit maybe a parabola that fits the data a bit so better. This would be a degree 2 sort of curve, or maybe it's a degree 3 curve that could look maybe something like this. Maybe this fits the data a bit better. Okay, and so if you remember how we actually did this, we started with x, but we converted it into this xp tilde matrix, right? Which is the first column was all ones. The second column was x1, x2 up to xn. And then the next column was x1 squared, x2 squared up to xn squared, up to x1 to the power p, x2 to the power p, xn to the power p. Right? So we've taken the data, the single scalar value, right, which is just the value on the x-axis here, right? And then we've created a higher dimensional representation of this. Of essentially, we've created these polynomial kind of powers of this data, and now we can fit a function through here. We would like to fit a function m alpha p, which is going to be the sum equals j equals 0 to p of alpha j, this is of x, from x to the power j, right? So now I can, instead of fitting just a linear function, I fit a polynomial function of the function of x, because I consider all the coefficients with these different powers, right? So if you remember, like, for instance, on the homework, I wrote that more complicated F2 function. There are other ways you can write these polynomial functions of x. You could say x minus 2 squared plus 3x squared 2 minus x cubed, right? So I can write it in other forms. So like I wrote it up here, right? And this doesn't exactly look like this red form, but you could try and simplify this, multiply it out, right? And isolate the coefficients. And so any polynomial function up to a certain degree, this is up to degree, so 5, because I have x squared times an x cubed, right? So it's something that's at most a polynomial degree 5. I can write it in this form, okay? And so the key then is to solve for this function, this set of parameters alpha 0 up to alpha p, right? And so the optimal that's minimizing the sum of the squared errors, remember, is going to be, we can solve this as a closed form, xp tilde transpose xp tilde inverse xp tilde transpose y, right? There's this closed form expression for this. Okay, and so what's going to happen as I'm increasing my value of p, I'm expanding this matrix and I'm getting more and more powerful functions, right? More and more flexible. I have more degrees of the polynomial, and eventually I'm going to fit this data here. So I'm going to fit the data so exactly. It'll eventually exactly go through every one of these data points, right? Right. So maybe ultimately there's going to be a function that looks like it's going to be pretty wild. Oh, that. Oops. All right. Let me. Okay, so eventually you can get a function that's going to go through basically every one of these data points, and the error is going to be 0, right? So if this is m alpha, let's say 7, right? So p is 7, then the sum of squared errors of x, y, and m alpha 7 is going to be equal to 0. I'm going to have 0 error on this. Okay. Yeah. So okay. So is this function, the orange one, is this going to be better than the green or the red or the blue ones? Yeah. So maybe, right? There are some applications in so geometric modeling, right? This is, you know how like the like if you look at the metal on a car and how it's kind of curved in this nice way and makes these nice, patterns, kind of that's designed by, often there's some more kind of but like classically these are designed a lot by fitting these specific so polynomials that interpolate actual all these data points. And what they do is they say, I'm going to set up a polynomial of degree degree, kind of some high degree polynomial, and then move around the data points until it has just the right shape. There's specific techniques of how to do this, and so sometimes that's the right thing to do. But in terms of kind of data analysis, this is probably not the right thing to do, right? Yeah, so if we're doing data analysis, so what makes a good model, right? So I've got a model, M, I'll just call it M, so alpha, right? And this is going from, let's say, R. so this is the domain of X, right? To some real values. So this is like the value Y, right? And I've got some, and perhaps I've got some input X, Y, right? So this is my data that I've got as input, and I want to model what makes a good model. Why would one of these models, like the ones I drew on the previous page, be better than other models? Yep. So we want to predict the the dependent variable. So why? Yeah. So what we would like to do is that if we have some, as I had said in the earlier lectures, we only have an X. We have some observations X, and we'd like to predict a new Y. We'd like to know how good is this prediction. So, okay, so great, this is good. That orange function I drew on the previous slide, for all the data I had, it was exactly predicting those values, right? So that seems like maybe that one is good, or maybe one of the other ones is good, right? So which one of these functions is better at predicting values, right? How would we think about that? Yeah.
My thought is if you overfit the data like you are, not all the values, you're not taking into account that you might not be accurate data, and you're like fitting your model to these errors. And so maybe instead of, you're saying there's no errors, but really your data has errors.
So yeah, so we don't want to overfit, and so we want to be so robust to noise, right? Yeah. So so these are so these are also important things, right? So like we're going to be talking about some view of something like overfitting, and then maybe on Thursday I'll tell you overfitting isn't quite the right way to think about it, but it's definitely it's definitely a common way of describing these issues, right? And we want this to be robust to noise, and this is probably on the right track, but this is not necessarily quite the way that these issues are often so discussed. Like one way of thinking about it is if I've got a function I'm predicting that's so quite curvy, right? And this went through some specific, so these, so data points. And so what I would like to do is to have a new value X here, and I'd like to predict M of X equals, so Y hat. And what this orange function is doing, right, is it's finding this value here and predicting to this Y hat over here. But if you notice just by kind of looking at this, there's this trend, this simpler trend here that the variables are kind of so increasing. And if I look from these two values in between it, right, the two values in between, well, the Y hat is a decrease of the Y values I have recorded for X values that are kind of on, say, X1 and X2, which are on either side of this X, right? So if I move this this prediction X slightly to the left or to the right, its value might be changing a lot, right? So in that sense, this model is not necessarily very so robust to the noise in the X coordinate, and this does play into so some decisions on so what is the best model. We'd like the slope the kind of the factor that how quickly the function can change as a function of x, we want that to be small. And there are techniques that we aren't going to discuss in this class. They discuss in, like the data mining class and the machine learning class, that try and say a good model should have smaller slope is one way of interpreting it. And so it kind of will give solutions that bias towards a smaller slope of the model. And that helps control noise in these x coordinates. We aren't going to necessarily approach it from that point of view in this course, though. We're going to assume for now that the x values are known, so like exactly. All right, so this is a good point, but we aren't going to kind of address, this particular problem. Okay, so the first point about we want to predict the dependent variable, and in particular, what we want is that to so the model mx to perform so well on so new data x. Okay, so data that we have not seen before. What we'd like is that when we get new data that we haven't seen before, we'd like the model to perform well on this data in the future, right? The goal is to learn from data and make a prediction on stuff we haven't yet seen. That's when this is useful. On the data we have seen, I already know what the answer is. I already know what the y value is. Okay, so what we would like, how we'd like to evaluate these models is how well they will predict, they will work on new data we haven't seen yet. How are we supposed to do that? We're maybe given a family of these models, and we're given as input this data x and y, right? But I know what the value is on these y's already. I've used, and I can fit or potentially overfit a model to go through all those data points exactly. How do I understand how well is this supposed to work on new data that I haven't seen yet? Yep.
We have a family of models from the sum of squared errors now, some that data set.
Yeah, so if I had a new data set, that'd be great, but this is the only data set I have. Yeah.
Maybe made some assumptions about your ways, maybe it's like one or something.
So another way of trying to work with this, so I've found the least squares error. Even with the polynomial model, I can derive a kind of a Bayesian inference or a maximum likelihood estimate, at least, view of this, where I say, okay, I assume the data came from some normal noise model in the y variable, and then find the most likely estimator under some family of models. And I can choose any polynomial for that, but I still will get that this will be the most likely estimator of that data. So but it's depending on whether it's the blue one, which is linear, or the orange one, which is a high degree polynomial. Given that family of models, the degree of the polynomial, those are the most likely estimators. I could try and do something like, okay, maybe I know something about what the variance is supposed to be on the data, and I want the model to fit so that I measure this kind of the variance in these residuals, and I want that variance to match what I think the actual variance is. You could do this. This is not kind of the usual approach to doing this stuff. Yeah.
Don't you test if like the coefficients A, B, C are equal?
Yeah, you can do something like something like a hypothesis test in statistics to try and say, is this model better at kind of under some assumption on the data than, you know, some other model. And you can try and do this, and there are ways to set this up, but this is really not the standard way to approach it. You can try and check individual coefficients, whether they're useful or not. Again, looking at individual coefficients, it's pretty messy. These things are really a joint optimization. So this is a lot hard. People have tried to do this. It's messier, more nuanced than it actually seems to do to look at individual coefficients, whether they should be there or not. There are ways in the Daymine class that are in the book that talk a little bit about this. Yep.
Could you just save some of the data?
Ah, great, great. So you want to save some of the data for later. Yes, this is great. This is the answer I'm looking for. Yeah, anyone else have another comment on this? Right, and so what we need to do in order to do this, we want to save some data for later. This involves that we need to assume that this data came from some distribution, and these are IID. These are independent and identically distributed from some distribution. And then we're going to save, you know, so some data for later. And this is going to kind of be breaking the data down into a training part and a testing part. We're going to take all of our data, and I'd like to kind of draw this as a picture here, right? So this is the idea of data splitting for cross-validation. Okay, I'm going to think of this data set as having n rows. Okay, and we'll think of this as having an x part and some y part here. Okay, and x could be one-dimensional, it could be like multi-dimensional, but I want to kind of keep in mind that there are these rows of data here where this is like x1 and this is y1, and these are kind of so these are linked together. X1 and Y1 have to stay together in this way. Okay, and the output of this, I want to split this into training data. Okay, and also testing data. Okay, and inside of here, we're going to have X, that's train, and Y train, and X test, and Y test. Okay, and so what I'm going to do is I'm going to randomly split. Okay, so I will want to randomly split, and the randomness is kind of pretty important here. And so the reason it's so basically this x1 data point might go into the training set, and then I might also take the next data point, and maybe this goes into the testing. The next two, these go into the training, right? So this one, these are going across, and then the next ones might be going into the into the testing, and so it's a randomly split of this data set. Yep.
Is there any way of knowing if your class has like IID in it, or is it something?
Yeah. So there are ways to. Yeah. So I'm emphasizing this randomly because the data is, if the data was actually completely IID, I wouldn't need to randomly split it because it was already, each row was independent of every other row, and I could just take it at some point and take the bottom half and the bottom half as testing and the top half as the training. This is not always the case, though. Sometimes you collect data over time, and the time of, the first ones are a little bit different than the last ones, or they're collected over a week, and the times a day, they're like your customers on your website, people shopping during, the middle of class, hopefully not, or have one pattern, or people shopping, at the end of, at the end of the night. I'm assuming it's like minor construction or ventilation issues, but well, the roof seems to be holding up much better than in the, so the MEB building. So, yeah. All right, does everyone feel safe in here? Yeah? Yeah, okay. All right, well, then we keep going. If stuff starts falling off the roof, we'll head to the exits. All right. So, all right. Yeah. So, so the end goal of what we're going to do, we're going to try and make an error and try and predict what's the expected kind of loss on like the expected error we're going to get on like an average, so data point from the data set. So it could have also been that the data set was collected in some way which was completely random, but then someone decided to sort the data based on the age of the person or the last names before you get to it. And so then there's some structure because someone sorted the data for you. They thought they were helping, right? So it's better to kind of randomly split this. Whether it's actually IID, we're going to work with that assumption that it's IID for all the analysis. This is kind of underlying all of the analysis we're doing in the class. The central limit theorem required IID to say you get more data points, you get a more accuracy. So what we're going to kind of assume it's IID in this case. Whether it is or not, I mean, it's in some sense it may be IID from some distribution, but you don't know what that distribution is. Okay, so we're going to try and learn something representative from our data. Okay. All right, so you do this split into two parts, and what's going to happen is we're only going to train the model on the training part, and then we're going to evaluate something about it on the testing part. And so this testing part is like new data we haven't seen yet, right? If we assume that all of the data, right, so X, Y is IID from some underlying distribution mu, well then X, because we did a random split Y test, then we can also assume that this is also IID from the same distribution here. Okay, so it's from the same distribution, that the test data is from the same, because we randomly split it, it's from the same distribution as we got the full data set from. And so when we evaluate on the testing data, that's a good representation of what data we have not seen yet is going to look like. Okay, and the training data has the same properties. So if we train a model and we know that it's like a maximum likelihood estimator based on the full data set, well, because this is a random split, then assuming that data set is big enough, it's also maximum likelihood estimator on the training data, which is also a representation of the model. Yeah.
Isn't there some kind of heuristic to determine the proportion of like the data should be training and should be testing?
So yeah, so this is a good question. I believe the first ever there's kind of not like a single sort of unified theory on this. The first time someone did it, I think it was a 70-30 split. That's pretty common. A 2/3 training, 1/3 testing is a common thing. 90-10 is also pretty common. In this lecture, at the end of the lecture, we might talk about some other variants of this once I get through formally defining this. Really what you want is that, right, I want to get an accurate estimate of how well I'm going to do on new data. How much error do I get on new data? How is this performing? And I need to have enough here so that if I apply a concentration of, some measure bound, that actually kind of makes sense. I'm getting a good estimate. My central limit theorem is converging to a good estimate of the mean with small variance. But I also don't want to leave out too much of my training data, because then if I don't have enough in the training, I'm not building, like a good model. And this is generally useful when you have a lot of data. No one came up with this until I think it was like Heilemann in the 1970s trying to do some work on recognizing characters. And he made this data set with hundreds of characters to try and recognize, is this an 8 or is this a 3, right? And before that, most statisticians worked with much smaller data sets. Computers weren't really a thing. And so data sets were in the size of 20s or 30s that you calculate stuff by hand a lot. And so you didn't have enough data to you didn't want to put stuff in your testing data. That didn't make sense. Data was much more scarce. Now we can get thousands of millions of data points, and both training and testing are both very representative, hopefully, of the pattern we're trying to do. Yeah.
So I'm assuming that for most computer models, you would multiple mixtures of training and testing, right? You're not just doing you're not splitting the one time.
If your data is large enough, is 100 million training points, and you're trying to train a pretty simple model, you probably only do one split. Sometimes in a lot of these advanced deep learning models, it might take $10,000 to do the training on the training data set. I'd rather only do that once. It might cost. There are some models I've worked with that cost over millions of dollars to train.
Oh, really?
They'd rather only do that once if they can only do it once, right? Yeah. So if you have a lot of data, you don't necessarily need to split multiple times. It's when you have smaller or medium data sets that you want to do multiple splits.
How do they find the different?
Yeah, so these are good questions. I think you're kind of jumping a little bit ahead of the lecture at this point. So let me kind of write down a little bit more clearly what this is doing. I think for some of you, you're kind of grasping this, and for some, maybe some details are missing here. But okay, so I first the first step here, one is to, first step 0, step 0 is to split, right? Step then 1 is to train. And so I'll write concretely, right? The alpha we're going to get is going to be from the training data. So it's going to be X train transpose X train inverse X train, running out of room here. Okay. So Y train, there should be a transpose there. Okay, so I'm just using the training data to train this model, right? So this is now a model M, corresponds with a model M alpha from training, from the training data. And then step 2 is I'm going to evaluate. I want to evaluate how well this model works on the testing data. So I'm going to evaluate, say, the sum of the squared errors on X test y test on m alpha. Okay, so this is so I'm going to take this m alpha, and this is going down here, right? This model is being evaluated against the testing data. Right, so the testing data is what this evaluation is doing. And for instance, I might want to report the root mean squared error on m alpha with respect to x test and y test, right? So this might be equal to this sum I equals 1 to n test. The number of data points, this might be n test, the number of data points, the m alpha, again, this is the model I've trained on from x, or how about I write this over x in x test, xi, minus yi, the corresponding yi squared, right? And I might take a 1 over n square root of this, right? So this gives me some sense of like the per error, per data point error I should expect, the root mean squared error. And this is done over this on the testing data, okay? Right, so I split the data randomly into different parts. I train it by just looking at the training data, and I evaluate it just looking at the, so by just looking at the testing data here. Okay. One thing we haven't really talked about is, I think I've probably conflated two things here, and that's how well, when I evaluate, what is that I'm using this evaluation for? Okay, so this is the procedure: split, train, and so then evaluate. Okay, and there are two things that were the two things that we're going to be using the evaluation for. One is how well do we expect m alpha, or some model that we can predict to work on new data, right? So I want to say if I get new data, I'm gonna make a prediction, and there's going to be some error, right? So if I look at what's the expected kind of a squared error, or what's the expected square root of the squared error, this is based on, say, the root mean squared error, right, of the model. I can give how well do I expect, how much error do I expect to get on some new data I have, okay? The other thing, which is slightly, so different, which is what we started with, okay, is how do we choose the best, so parameters, okay? So in general, in machine learning and data mining and in these supervised things, you have often a number of parameters in the models, and the alpha, we're kind of learning by fitting something onto the data, but there's also these, like hyperparameters. Okay, so these hyperparameters, and this would be like the value p, okay? right? So this, for instance, is the degree of the polynomial. Okay, so how do we choose the right degree of the polynomial, right? And so these are different questions here. They're kind of similar, but they're not quite doing the same thing. Yeah, question.
Can we also use that to evaluate which explanatory variables are important? I don't know that are relevant.
Yeah, so this is kind of tricky to do. So you could, yeah, so you could, so how you would try and do this, the proper way of doing this is actually, let's say I've got, so like some model with so like in the high dimensional regression kind of a version we're talking about. Let's say there are 10 different attributes you're looking at, and you'd like to say which of those are the most important. You build a model and all of them have some sort of coefficients, right? How you would need to do that is you would need to actually look at every subset of all possible sizes and see which one of those generalizes the best. If you were to just pull out one variable, one attribute, and then say, let's build a model not using this attribute, and if the model does basically as well or almost as well, then or even better without this attribute, then I can not use this attribute, you might say. The problem with this is there might be another attribute that is basically serving the same purpose, and I could use either one. And so just because I threw that, if I didn't use that one, it didn't kind of show up as being, the model was basically doing as well. Doesn't mean that it wasn't important. It just means maybe I could have replaced this with another attribute that I already have. And it's more complicated than that. It could be there's a combination of 3 attributes that could be used to replace this one. And if I do this test individually and I try and check each of those, say, group of 4 attributes, any one of them I can remove, but if I remove any 2 of them, I start to really lose performance. So if I do this test individually on all 4 of them, I might say, okay, I'll throw them all away, and then the model does much worse, right? So it's a little, so with these trying to draw inferences on individual attributes is kind of tricky here, because these are really tied together. There are techniques for doing this where you try and find if there's like a linear association between these. If you have a linear model, if they're like not like linearly independent, you might be able to try and factor these or find a subset which is useful. And so there are ways of doing this as pre-processing. For linear models, this is somewhat understood how to do this. For nonlinear models, it becomes much more complicated, right? Because in a polynomial model, for instance, the relationship between these, I'm looking at different powers of different variables in some model and different combinations of those, and how to factor those out becomes even more complicated. There are methods that will try and automatically do this. And if you look in the book that we won't go into this class, there's a technique so-called lasso, which will try and find a model that does well with a small number of non-zero coefficients in the model. Okay, it's not saying those are the only correspond with the only parameters which are important, but it's a set of parameters which does, so fairly well. Okay, this, if you take the data mining class, we'll spend a lot more time on this, and it's in the book if you want to read it. But these are interesting questions. It's not a simple answer, right? Okay, okay. So we want to evaluate. Evaluation can mean these 2 different things. How do we choose the best parameter, right? And we can check the different values of P and see which one is doing the best. And we can also say how well is it doing on new data, but we can't do these both at the same time. Yeah, question.
Is there a way to like find a gradient with respect to the hyperparameter?
Yeah, okay. You want to think about,
You just have to try like everyone.
in this context, we're going to try everyone. We'll talk gradients, we'll talk about after break. And in this case, it's very easy to define gradients with respect to alpha. Usually hyperparameters are things that it's harder to define the gradient with respect to. And they may not be what's called convex with respect to, and you kind of need to try all of them. Sometimes they are, and you can do stuff. And then in deep learning, you just, everything is a regular parameter and you put gradients and everything and you close your eyes kind of and hope for the best. I mean, I'll give you a little bit more context to that, but you can consider doing that. In this case, we're not going to consider this. We're going to think about, we're just going to try all the different parameters, right? And this is typically, in a lot of cases here, aside from deep learning stuff, where there's these nice mechanisms to kind of put all this together, the standard strategy is just to try a bunch of parameters. Sometimes these are continuous, and then you have to kind of do some tricky search, trying to find the right answer when it could be any continuous value. But we're going to focus on these discrete values, like the degree of a polynomial. Okay, and so it can be up to the number of the data points at most, but usually you'd put a cap. At some point, like a degree 10 is pretty crazy. You very rarely want to use like a degree 10 polynomial. So then there are only like 1 through 10 different values you'd want to consider, and probably even less than that. Okay, so there are two things we want to do here. Okay, and you do not want to do both at the same time. Okay, you do not do both at once. Okay, so the problem is, if you are using the test data to train a parameter, you're essentially doing training on this parameter P. So then the same way that if you had a really high degree polynomial and you fit through all the data, you're kind of something like overfitting, or you're choosing the parameter P so it does well on your testing data, which makes the testing data not a fair reflection on how it will do on new data. Okay, so if you actually want to do both of these things, you need to do a three-way split. Okay, okay, and forget what there's different terminology for this. Let me see if I can. I don't remember what I called it in the book, but okay. So we have this Y, and now we're going to have three different sort of data sets. Often when you do this, you might do 80-10-10. Often this is when you have a lot of data. So you would have the, this is X, this is X train, Y train. Then you have a X test, Y test, and then you have like you'd have like a validation set. Okay, so again, what you would think of doing is you would have a bunch of these training data that you're choosing, and these are all going to be mapped into here, right, at randomly split. Okay, then you have the test data, which you are pulling out at random here, and these are being mapped to here. I just think students, if I don't draw this sort of picture, this is always kind of confusing everything that's going on here. And then there's also the validation data, okay, where you are also pulling these into this last set, okay? And so now what you would do is you would you'd have kind of three phases here, right? One is train. Two is to choose so hyperparameters, right? By saying how well that's doing on the testing data. This is with the test. So this is with the X train, and then finally step 3, you have the so you have the evaluate on the validation set. Okay, and so because this is a random thing you've held out, the held out set from this whole process, you actually want to view this kind of whole procedure here as all part of the training, right? So this whole procedure involving the training and the choosing of the hyperparameters, right, is all part of the training part of it. I'm choosing like alpha. Basically, this one allows me to choose alpha, and then this step allows me to choose p. But both alpha and p are parameters in the model somehow. They're somehow from a family of models of polynomial models in general without specifying p. I have the coefficients alpha, and I have the p, the degree of the polynomial. And then I have some validation set where I finally say, okay, how well do I expect this to actually work? All right, so kind of, I think it's important to keep these three things kind of separate from each other. All right, okay. What left do I have to do? All right, so there are a couple more comments. You guys are asking a lot of great questions today. And so there are a couple of things I want to talk about. We kind of covered already about how to split and some variants on that. Maybe I'll come back to that, but I've got a kind of a small demo in Python. So maybe we'll jump into this first. But if any kind of this big picture, this question, this kind of makes sense where there are these two different things you want to do, and this works because you're holding out data and you want to see how well it will work on new data you haven't seen yet before. And because you assumed all your data was IID from some distribution, if you hold data out, then that should be a good representation on how well it will work on data you haven't seen yet. That notion is, so how well is it going to generalize to this new data? Okay, and this concept is like the primary way most machine learning and data mining, especially machine learning with supervised machine learning, they say, how good is this working? Okay, and there are these so how many people have done something on, so Kaggle? Have you heard of this? It's a website, right, where there are these data sets and challenges. Say, here's data set, I would like you to try and, predict, there are lots of these challenges, and what they will do is they will present the training data, and then they will have some test data available in different ways. And the best way to do this is to allow someone to evaluate the model they built on the training data on some test data they have. So kind of they have kept, or they say, here's evaluate your model on this test data and see how well it's working. And there's like there could be like a leaderboard of how well different people's algorithms are working on this. And then at some point they will freeze the leaderboard and say, okay, here's the best solution. What they should do, and in some cases what works, is they have a final validation set that they don't let anyone know until they have closed the contest. And then they say, okay, how well do the best algorithms do on this final validation set that we've held out at the end? If they don't do this, people will overfit onto the test set that's available, and they'll overfit to the onto the leaderboard. Sometimes who's done best on the leaderboard on these little contests does not do the best on the validation set because they've somehow overfit to this. They've submitted a lot of different models. And they said from all those models they've submitted, they figured out which ones happen to work the best. They just randomly tried different things. And it overfit something to the test data, but it didn't actually work well on the actual thing. So you have to hold out another data set here. Okay, so if you kind of are not careful about this, then you can kind of run into some problems here. Okay, and there are certain tasks within machine learning, like there's these problems like computer vision with ImageNet and CFAR, which is recognizing these kind of like these like handwritten numbers, digits, trying to predict what they are. That there have been countless hours and people working on these and coming up with algorithms that they've kind of overfit to the solution, to the what. Typically there's a typical way of splitting them, and they say, here's the typical way of splitting, train on this, see how it well works on this set which is held out. And they've been doing that for so long that they've kind of, the stuff that happens to work best in the test data wouldn't necessarily work best on some new data. And there have been some studies where people have tried to collect data like this and say, okay, some other data that wasn't in the original data set, how well do the methods actually do? And they don't do quite as well as people would hope they were doing based on this test train split. So kind of keeping this separation is kind of an important thing to keep in mind. It's probably true within companies do this internally. They have more advanced data science companies have a lot of internal data sets they've collected, and they try and keep this separate, but they might not be. If they're not careful about it, then they will end up overfitting to the data they've collected, and it won't reflect necessarily what other new processes will happen here. Okay, let me go to this example here. Okay, again, it's linked off the web page. And so your homework will have to do something kind of like this on a larger data set, but this will be a small one that'll kind of illustrate it well, hopefully. And we're going to do some plots here. Okay, so I think I took, this is another data set I created, and I've already split it here, right? So I happen to take, it's got the training data has 6 data points, and the testing data has 3 in this split. Oh, I need to do this one first. Okay, and then I'm going to plot these. Okay, I'm going to plot these here, right? And so the training data was in blue, and the testing data is in green here. Okay, and so I'll fit models that will try and do well on the blue data, and I'm hoping it's going to also do well in the green data, right? And I can choose different polynomial models here. So I just built one I do a polynomial fit, this one function in Python I mentioned that fits this, and you can just put in a parameter p here, and I've run this with parameter 2. I can calculate the residual, I can get the squared error, 0.91. Okay, that's the sum of the squared errors. And here's what the curve looks like. Okay, so a polynomial of degree 2 does, I think, a pretty good job. It goes through the blue data points almost exactly. Not quite exactly, but pretty close here. And doesn't do pretty, you know, it does okay on the green ones. If I, yeah, nope. Oh, okay. Yeah, let me, on an iPad, sometimes it's a little weird typing. I don't want, you cannot set P to equal a smiley face. It doesn't do anything. Okay, and, okay, so if I said a 1 degree polynomial, right? It just fits this line here, right? And you can see the sum of squared errors on the training, on the testing data is like 5.8. So this is larger, right? So this says the linear model is worse than the degree 2 model. And kind of viewing it, I can see it. It seems near the edges of the data, it's kind of deviating more, right? It seems like the degree 2 was a bit better. Let's try degree 3. Okay, and okay, this one, it's a bit similar squared error. I forget which one was bigger, but this is a similar. I'm kind of still only getting one curve in here. Let's see what happens if I do 4. Degree 4, what's this going to look like? Okay, this is, okay, my sum of squared errors has gone up. In particular, on the inliers, the data, the green points inside the range of the blue points, right? I'm probably doing pretty well. In fact, I'm going right through one of them. But this one on the outside here, there's a pretty big gap now. Remember, it's the vertical distance, not the closest distance. So the vertical distance and the y-coordinate is getting big. Let's try a larger degree polynomial. What should I try? 8? What? 15. Well, okay. Let's. All right. You know, you guys are the boss, so it's, you know, it gave some error here. All right. And okay, well, you know, that was a good. Yeah, this is, look, it went through the blue data perfectly, but it's like it completely avoided that green one up there. You know, that was probably not a good choice, right? So here, cross-validation is telling us that we have, you know, the error is much larger here. This is not doing as well, right? Yeah, so this was a pretty good example, right? I'm exactly fitting the train data, but on the testing data, I've kind of maybe intentionally avoided it, right? So this is why you don't want to have a really high degree polynomial. Great. Okay. So on Thursday, I've got like, if we have time, we want to do this. I have a demo plan that is computing this a little bit more so robustly, and we'll see that maybe we do want to go some cases to really high degree polynomials. Okay, if we set this up to like 200, and it's not going to work here because it's using kind of you need to tweak stuff a little bit to get this to work. But if you how I implemented it, but if you set this to like 200, it might actually start doing so like good again. This should be kind of surprising. Okay, so that's the preview for Thursday. Okay, I also want to point out one other thing. Remember on the degree 4 one, we were doing pretty good at the 2 green points in the middle of the data, but we did poorly on this one outside of it. Okay, so maybe you think, okay, well, if the testing data is completely inside of my data, it should still do pretty well with higher degrees, right? That might make sense. This is a one-dimensional sort of kind of intuition that I think does not necessarily work well in when you get into higher dimensions. Okay, in higher dimensions, higher dimensional data, which a lot of data ends up as higher dimensional. We just can't plot it nicely like this. It's hard to be inside of the training data. There's a lot more dimensions and ways you can go outside. And we'll think about high dimensional stuff later in the class, and maybe this will make more sense, but it's a lot harder to be completely inside of your training data in higher dimensions. So that intuition that, okay, maybe it works well inside if I keep the polynomial not so bad is not necessarily going to generalize to these more complicated examples. Great, okay. So you'll do something like this in your homework, and you'll get to play around with this. And so they've given you some basic starting points for this. Okay, I want to. Okay, let me say one more thing about splitting the data. One more variant I'll mention, which I think is worth mentioning, is kind of, there's a lots of questions of, how to split, and the first answer is random. If everything is IID, you technically don't need to do random, but this is kind of safer in case someone sorted your data for you, right? Or if it's not quite IID, but you want to model it as, okay, my customers are kind of have different patterns, but those are my customers, that's what I want to model. Okay, so, but then there are questions of, 80, 20, 70, 30, 90, 10, okay? And really it's the answer here is, I kind of need enough training for the model to do well, and I need enough test to predict. Okay, the testing probably needs less. Why this is because the testing is typically looking at a one-dimensional value, just the sum of squared errors. And I want that estimate to converge, and that's a one-dimensional kind of estimate I need to converge. The training is over models that are often higher dimensional, and so they probably need more data because they're trying to estimate a higher dimensional sort of parameter space here, right? This is estimating the sum of squared errors. This is in R. This is estimating alpha. This is in RD. Okay, the D dimensions means, okay, it's a more complicated space. So probably this grows with D, right? So I need something like of extra factor D more training examples to do well in here. Sometimes it doesn't grow with D. You can ask me offline about some thoughts on this. It depends on what you're training, but you still typically need more for the training than you do for the testing. Okay. Okay. The last question: what if your data is so small? Okay, and I don't really want to spare much for the training or testing, right? So this has mostly been in the context of very large data, but people want to do cross-validation when they don't have a good statistical model to otherwise try and evaluate this. For instance, I've worked with loosely some projects that deal with like scans of like a brain, and these MRI high resolution scans, maybe over multiple different patients multiple times. They might cost like tens of thousands of dollars per actual data point they have, and they're very hard to collect. And so you might have 10 to 20 sort of data points, right? N equals 10, or 20 in this range. And so I want to build, and these are complicated data sets. I want to build a somewhat of a complicated model on the training data, but I still want to be able to evaluate. So how would I do this? I don't want to keep any of my data out of the training. I want to build the best model possible, and each one costs like $10,000. I'm not going to throw away $10,000 to train. I don't care. Maybe my evaluation is not quite as good. I want to use that model in my training. So what they do, what's common is called leave one out, LOO cross validation. And what they'll do is they'll do n different splits, in this case, of n minus 1 train and 1 test. Okay, 1 is the smallest I can do on the test, but I can do this n different times, and then I can take the average. Okay, you can do other versions of this, like 10-fold cross-validation, where I split the data into 10 different sets of, each is 10%, and I always train on the 90% and evaluate on the 10%. There are a couple of things that I can take the average, how well it did on the data I've held out to test. But then which model do I actually use? You probably retrain on all the data in this case, but you're just kind of get a sense of how well it works. And now I've kind of mixed up my training and testing, so my evaluation is not quite as good, but it's some way where I can train on most of the data and evaluate on still all of the data, because I'm still at some point keeping out every single data point to test on and average it. This is more expensive, but if my data is small, well, then that wasn't as big of a deal. If the data is really big, you don't need to do this. Okay, so the bigger your data is, you do 1 split. If it's medium size, maybe you do like 5-fold or 10-fold. And if it's small, you do like this leave 1 out, which is like n-fold cross-validation. Okay, we'll stop there, but I can take some questions.
Is the leave 1 out validation, is that even better? Like, isn't better to do that even before?
If you had unlimited amount of time, this is probably, and you wanted to train on, say, the best model I could do, this is the best approximation of that, because that uses n minus 1 of my data points. So it's probably better. There are questions, there's some cases where some people argue it's not better, and there are other things you can do when you have really, really big data sets, because you might get duplicates and other issues that complicates this. On small data, it's better. On big data, people typically don't use it, even if because the training and the test size are large enough already to be good representatives of the underlying model. Great. Oh, what do we average? Yeah, I see the question now, Anissa. The average is over the n splits. So each split, I do a n minus 1 training points and 1 testing point. And I evaluate how well it does on that 1 testing point. And then I take the average over those outputs. Great.